Sure. Oh.
We can start? Good morning, everyone, and warm welcome to the day 3, the final day of PReMI 2025. We are delighted to begin today's proceedings with our morning keynote session. May I request the session chair, Professor Susmita Mitra, to kindly come forward and conduct the session. I also invite our distinguished keynote speaker, Professor Subbarao Kammampati, to join us on stage for the session.
Hello.
Good morning, everybody. So it is my great pleasure to welcome you all and to welcome Professor Kambapati as the keynote speaker of today, day 3. So Professor Kambapati is a professor at Fulton School of Engineering, Arizona State University. He is a professor of, he studies fundamental problems in planning and decision making, motivated in particular by the challenges of human-aware AI systems. He is a fellow of Association for the Advancement of Artificial Intelligence, American Association for the Advancement of Science, and Association for Computing Machinery, and a recent recipient of the AAAI Patrick H. Winston Outstanding Educator Award. He served as the president of the Association for the Advancement of Artificial Intelligence, a trustee of the International Joint Conference on Artificial Intelligence, the chair of AAAS Section T, and a founding board member of Partnership on AI. Kambapati's research as well as his views on the progress and societal impacts of AI have been featured in multiple national and international media outlets.
Thank you. Thank you. Do I proceed? Thank you all. First of all, thank you for getting up on Sunday morning, apparently after a sumptuous Bengali dinner. So it must have taken quite a bit of an effort. Thanks for showing up. So I am going to talk today about the whole background, essentially to some extent, and as well as our work on understanding large language models and their planning and reasoning capabilities. That's what this talk is going to be about. Just see. Okay. So let's see. I come from the planning, automated planning, way before when I started my PhD, etc. So planning essentially is generating a course of actions that will achieve certain desirable goals, and in some sense, all the agents, first of all, AI agents, any intelligent agent has to figure out how to put together a sequence of actions or a policy to achieve desirable goals. So that's my background. And so from that perspective, when I actually look at how do LLMs reason, to some extent, I'm actually focusing on the specific part of planning, which is a particular form of reasoning. It's a form of reasoning about change and dealing with actions. So in a way, how do LLMs reason is actually more about how do LLMs plan. That's the kind of thing that I'm going to discuss. And so what I'm actually going to do today is sort of walk you through, again, because I didn't quite know exactly what sort of background everybody will have. I see Mausam showing up suddenly. So what I was going to do is actually walk you from like the beginning of LLMs, the standard LLM models, and then go from there to reasoning models, and then see whether they have the capabilities about planning and reasoning, and if in fact they're showing the behavior, why might that be actually happening? And depending on the time, I'll also try to get into some of the recent issues with the reasoning models, such as these think tokens that they output, and see whether or not the think tokens have any semantics. So that's what I'm going to do. So it's a long amount of stuff that we're going to do. Let's see how far we can get through this. So first things first, I assume that everybody understands that a narrator-narrator model. How many of you know of narrator-narrator models? amplifier circuits, etc. So a simplified model of LLMs that you should at least use for sanity check is LLMs or n-gram models. And n-gram models have been around forever. Claude Shannon actually looked at them, but mostly he looked at unigram, actually he looked at bigram, trigram sorts of models. That means given n-1 words, what is the probability distribution of the nth word? That's what you're trying to learn, okay? So the interesting thing is LLMs can be thought of in some level as n-grams and steroids. People were talking about, bigram, trigram models. Even the old poor ChatGPT 3.5 is a 3001 gram model. If you think of the context window as 3000 tokens, then essentially given 3000 tokens, you're trying to predict what's the likelihood of the 3000 first token being one of the vocabulary items. This is what you want to understand. And then basically, all n-gram models basically train on statistical properties of the language. And so in this particular case, we're training on all the, the language that's available. For now, think about English, but pretty much any of the languages. And so again, you need like an example, and so here is a simple example of a sentence that you might be learning from autoregressively. All other IITs are on eternal of IIT Madras, apparently just a randomly generated sentence. And so basically, the system is essentially trying to train, seeing the first word. The current model tries to predict the next word, and then checks what the actual sentence is saying, sees the difference between the two words. Now, the difference between the two words are the vector difference in the embedding space, and then he essentially tries to minimize that error through backpropagation methods and so on. So for example, if it uses the current LLM model might just say all, as soon as it says all, it might actually likely say that the next word is going to be right, all right. Except the guess is right, correct is other, because in my sentence, all other is the next word. So the error is other minus right, and this difference between the words is actually a vector difference in the embedding space that you're going to minimize. That's what you're trying to do. So this is it. Essentially, everything that's important about LLMs, you can actually make sense at some level with respect to their n-gram nature. So the question, of course, the interesting thing, of course, is this count table. Of course, if you're doing n-gram models, you essentially count, the prefixes, and for the prefix, what are the likely next word that's coming, and keep track of the usage statistics, the frequency statistics. This count table becomes ginormous when you're having 3001 context window. So first of all, remember that if you have 3000 words, if you assume 50,000 word vocabulary, a sequence of 3000 words essentially is 50,000 power 3000 possible combinations. So you ask Google, it will say it's infinite. Okay, so these many rows there should be in the table, and then for each of them you are then trying to figure out what's the next word. And what happens essentially is you have extremely sparse amount of data, because the likelihood that you will see the same 3000 words a second time in your entire life is basically zero. Okay, and then 3000 is what ChatGPT 3.5 is. Now we are talking about million token windows, so keep that in mind. So basically what happens, of course, is you try to, instead of keep track of these things as a an actual table, you are learning it as a large a neural network, and that essentially compresses this table. And anytime you do compression, you are in some sense doing generalization. Okay, because when you compress in the original table, there would be, like, if you have 3000 word sequence and there's a particular word that occurred in your corpus, it's most likely that you will never again have any other word with exactly those 3000 words preceding it. And so only in one word you will have one, and everywhere else it's zero. So the probability is fully for that word. So it looks as if it's obviously a degenerate table. When you actually then train it with the neural networks, it basically approximates this table. So the one actually becomes less than one probability, and many of the zeros will become more than zeros. So in essence, you kind of smearing this probability, and you are effectively doing some sort of an abstraction. And so, for example, if you have 3,000 word sequences where the 175th word in the first one is red and the 175th word in the second one is mauve, you might say both are the same because red and mauve are very similar. So this is the kind of thing that is happening below the hood in the LLMs, and it's kind of very useful to understand this because a whole bunch of things about can LLMs do hallucination, can LLMs do something else, etc. You should first try to see what would n-gram models say about it to some extent, and that sort of gives you quite significant leverage in understanding where you're going to go. So given that, now let's start talking about if LLMs are n-gram models, what do they do? Obviously, given the prompt, which is some k words long, it can be 3,000 words, a million words, etc. It's trying to predict the next word, and next word autoregressively using this particular training, this train network that it has. It's useful to compare it to retrieval in databases. We all made fun of databases. Any self-respecting AI person has made fun of databases. It's like a boring thing to do. But the great thing about databases, they never hallucinate. They only ever give the record that you put into the database. If you want hallucination-free technology, it exists. It's called databases. Okay. And then you think about information retrieval. What is information retrieval? Information retrieval allows for a query to be keyword-based, and then you are essentially comparing that keyword to the document similarity, and then the documents that seem to have high similarity to those queries, you bring them out. In the case of information retrieval, you are allowing the query to be imprecise, but the answer is essentially never made up. If you go to New York Times archive and give some names, some words, it will only ever give you the files that actually exist in the New York Times archive. Nothing is ever made up. Okay, there's approximate retrieval. So there's basically retrieval in databases, there's retrieval in IR systems. And compare this to what happens in LLMs. What LLMs do is after you give whatever is your query, written obviously in some language, it can actually be SQL. It doesn't really matter as far as LLM is concerned. It then starts generating next word. So in some sense, it's constructing the answer on demand after you gave the prompt, and so it's not at all surprising that it makes up stuff. Okay, it's basically both it's the creativity. If you can think of the fact that it makes up an essay as wow, what a creative thing it is, and if you are in a foul mood, you say why did you make up stuff? And you can't get to have both things essentially. In fact, my joke is that imagine you go to a court of law and you are a witness and you are being sworn in, and you say, Your Honor, I'm a very creative person. The first thing the judge will say is get out of my court, because you really don't want creative witnesses on the witness stand. The thing is, of course, humans can both be creative and factual. The interesting thing is it's not like LLM is suddenly going to change its this operation. It's basically doing this sort of a completion. And so keep this in mind. This idea of generating a sort of sequence of words based on the prompt, I call that as approximate retrieval, because the kind of thing it generates is not perfect recall, it's not a perfect retrieval, but it's very much dependent on the data it's been trained on. If you change the data, its completion changes. So think of this, it is somewhere between retrieval, but it's not perfect retrieval, but it is something, kind of what I just made up this word called approximate retrieval, and that's sort of stuck. In fact, in NeurIPS, Melanie Mitchell was giving a talk, and she had actually a whole entire slide on approximate retrieval, and I felt good because I made up this name and it's going to stick. But it's a useful thing to keep in mind. And in fact, if you think of the NY Times OpenAI lawsuit, essentially New York Times saying OpenAI copied us, actually, it's very hard for them to show the copying part by just showing that, look, you actually exactly gave our story. It so happens that in large enough training cases, sometimes there is a non-zero probability that you'll almost, memorize the entire article in some cases. And those are the things that they were focusing on. Keep that in mind. Now, if you think about it this way, hallucination is a feature, not a bug. You are always supposed to hallucinate. My way of thinking about it is LLMs always hallucinate. Sometimes their hallucination corresponds to your reality. In those cases, you feel good. Do you see what I'm saying? And so if you look at it that way, it's a feature. And you can use it for when you need hallucination, when you want to create an idea, LLM is your friend. When you want factuality, you are stuck with the fact that this thing will make up stuff. And you can put some badges, some patches to stop it from going too much beyond some things. But essentially, it's an n-gram model in the background. Okay, if you think of something like, oh, but my friend said RAG apparently takes care of all this stuff, what your friend is basically saying is RAG is LLMs calling Google. And remember, Google doesn't make up information. Not the current Google, the old Google used to essentially take your query and essentially take some document that exists on the web and provide that to you. Right now, what RAG would do essentially is that document will then be put in the prompt window so that LLM summarizes that. The idea is when you are summarizing, maybe you would not be hallucinating as much. There's no guarantees. In fact, summaries are made up. In fact, when people say LLMs summarize papers very, very well, it's because they never read the original paper. If you haven't read Ramayana, any random summary of Ramayana looks great to you. Do you see what I'm saying? And in fact, that actually gets me to this cartoon that I have there, that the impressive factuality of LLMs is partly based on the fact that the person doing the querying knows the answer. If the questioner doesn't know the answer, then they just have to take it in face value. In general, when you ask Google for a query and it gives an answer, you have to trust the source. Otherwise, you can't. If you are again going to check after ChatGPT, go to Google to check if the answer is correct or not, the whole point of having ChatGPT is wasted. Okay, so anyway, very many years back, I think by I understand it's like 23, when New York Times was asking various things. So I made my bucket list. I was a quotation of the day for a day, based that LLMs and hallucinations, that when factuality is paramount, I would not depend on what the LLMs say. Okay, we do get through where sometimes an essay looks like a good essay, you can get by with it, and so you can use LLM. So if the factuality is paramount and there is no way of verifying it, you are in trouble. You have to keep that in mind. The other thing that I want you to understand basically is LLMs are essentially a form of generative learning systems. What's generative versus discriminative? Generative learning systems learn the distribution of the data so that they can sample from that distribution. So the difference between can you check whether this essay is a good English essay versus can you write an English essay. So writing an English essay is generative, and just checking whether it's good or bad. Teachers don't necessarily have to know how to write good essays. They just have to grade it, right? That's a discriminative job. But if you're also a good generator, that kind of helps things. So generative machine learning systems basically capture the distribution. Style is a distributional property. It's in the style of Shakespeare. Doesn't necessarily mean it's exact copy of Shakespeare. It looks, in iambic pentameter, it looks like something plausibly like what Shakespeare would have written, potentially. That's the kind of thing generative systems are good at capturing. The problem with factuality and correctness is that style doesn't guarantee correctness. Correctness and factuality are instance specific, whereas style is distribution specific. To the extent you learn the distribution, you do well on the style, but not on the correctness. The sad part is for us humans, correctness is easy. It's a style that's hard. We all can kind of say, how hard is really Macbeth the story? It's pretty obvious stuff that, if you know enough of mythology, you can make up that story. It's the damn iambic pentameter that I can't get my head around. Now it's completely the opposite. Anybody can write iambic pentameter, right? Because ask ChatGPT. So, in the old days, the way to impress your boyfriend or girlfriend is to give them a poem for their birthday. Now you do that, you're like a bozo. Because they'll say, you couldn't even care about doing something useful other than just prompting the ChatGPT for my birthday card. That's why we are here. Suddenly, our assumptions have just turned on the head. Style became easy, correctness became hard. And we are used to a world where good style implies good correctness. And so we keep getting surprised. How can something in good style actually be incorrect? It looks so much like Shakespeare. How can it not be Shakespeare? This is the part you have to keep in mind. So by the way, that same thing that I was showing you earlier, I made a t-shirt. So I don't have a startup, so I sell this t-shirt to make my small million rupee investments. So anyway, that basically just says that the entire factuality and reasoning powers depend on you actually knowing the answer. And if you don't know the answer, you're in big trouble. Surprisingly, yesterday or day before, a particular tweet went viral, or somebody else was saying that GPT 5.1 is amazing at a lot of things I am unqualified to judge. That's exactly what happens. Do you see what I'm saying? How many of you heard of Gell-Mann effect? Murray Gell-Mann is a great physicist, and he would say that any given day, you open the New York Times, and if you're a physicist, you'll read New York Times wrote something about superstring theory or something, and say, oh my God, how stupid is New York Times? It got this wrong, it got this wrong, it got this wrong, how can it be? And then you turn the page, and there's an article about economics, and say, oh, that's how economics works. Which makes no sense. If in fact they got the physics wrong, they also got the economics wrong. It's just that you don't know economics, you assume what New York Times says is right. You know physics, you can actually question the correctness. So if you, in your area, it becomes harder to be impressed with LLMs. In the areas that you are not part of, it'll be easier to be impressed with LLMs. In general, I tend to say that what LLM technology, frontier models put at your fingertips is the humanities knowledge. And you are impressed because you don't know this, but that doesn't mean humanity doesn't know it. Other people knew it, you just didn't know it. And because it's like right away available at your fingertips, you are very impressed. And it's a great leap in making access free for us, right? So that's a very useful thing. One last thing before I go into the planning part is memory effect is important to understand about LLMs. You have to understand that whatever they are doing, one of the things that people tend to make is computational complexity analysis in understanding what LLMs are doing. If you're trying to, if your prompt is actually a problem, you would think that maybe it is actually solving the problem. What it's really doing is essentially completing. Every model just completes the prompt given the model parameters that it has learned, right? And so you have to understand that it's basically the memory effect explains what has been called the jagged intelligence. You can have essentially a model doing very well now on International Math Olympiad problems and yet fail on very simple things. There's a guy called Vince Konitzer in AI who's actually you should follow because he basically spends time playing with these models to ask them silly questions and make them fall on their face. This one is not actually the one that he gave. It's on the right-hand side. It basically is asking ChatGPT 5, look, Amazon sent me my left shoe instead of my right shoe and my right shoe instead of my left shoe. Tell me what should I do? And then the model says, oh, that was very unprofessional of Amazon. You should pack the shoes and you should do all these things and send them back. Right? You can laugh. The interesting thing is Terry Tao is a mathematician. I understand mathematicians are absent-minded, but I can't imagine him making this mistake either. Okay. In general, we tend to have these knowledge closure assumptions. You think that if somebody can do integration by parts, they can do multiplication fine, okay, and division fine, etc. That's just not true for a memory-based trained system like LLMs. They can be extremely good at the stuff that they've been trained on the distribution of and egregiously bad on something outside of it. So what we are doing, every industry tries to do, is fine-tune them on their data and hope that maybe it will basically save the day. And that the variations of them won't actually wind up making them get caught. So this is LLM 101 as far as I'm concerned. You should just have this in trying to understand what they do in everything else. Now I want to get into planning, right? So basically, when standard LLMs came along, before the reasoning models, people are already writing papers. One of the nicest things you can do LLMs is there's a template for title. LLMs are zero-shot XXX, where XXX is your favorite task. And you write it, NeurIPS will mostly accept it. Because in general, positive results are very nice and warming of your heart. And so there are lots and lots of these papers. Most of them more or less should be consigned to the dust heap of history, but they got in and they actually do get well cited. So there was a bunch of these papers about can standard autoregressive large language models plan. They're already saying they could, which is actually very surprising given what I was telling you about standard LLMs, because they're essentially n-gram models. Why would they actually be able to do this well? And in particular, for a plan to be correct, if you actually execute it, if it actually gets into states, if you're executing plans in non-ergodic worlds, which essentially a non-ergodic world is a one where an ergodic world is where you can reach from any state to any other state in positive probability. That means there's no death. Okay, non-ergodic worlds, basically you can get into a state from which getting out will be very costly, and planning is exactly important when in fact you have non-ergodic worlds. And what we'll find is LLMs are actually very good when planning is not needed, because they can retrieve plans and then just basically splice them together. And if there are no interactions, they might get good accuracy. Otherwise, they die. That's what we start finding. So when we got into this work back about 3 years back, we basically looked at this idea that if you think of system 2, system 1 analogy of human intelligence, LLMs, based on what I've shown you, can be thought of as a giant external system 1 for the humanity. They've been trained on the entire humanity's knowledge traces, basically whatever is written in language, and then they essentially can basically kind of, given a prompt, they can get you nice completions. Planning, etc., is generally considered a system 2 ability. And how did suddenly system 1 start doing system 2? Could they actually possibly do? So we spent a bunch of time trying to show that, in fact, there was really, if you take very simple planning problems, one of the simplest ones are actually putting blocks in one configuration to a different configuration. You can also do logistics problem, which is basically sending stuff from one place to other place over trucks. These are all the toy problems that planning people used to look at. We basically took a bunch of those benchmarks and the problems from them and then just fed it to GPT 3.5 and whatever else is available at that time, and they were dying pretty badly. And we then kept continuing. When GPT-4 came along, we did that for that too. And in general, we found that they do very badly on these kinds of planning problems. Furthermore, even if in fact they improve, like GPT-4 did better than GPT 3.5, one thing you could do is, if you had a memory-based system, you have to ask yourself, are you memorizing the answer or are you solving the problem on hand? In general, this is an issue. If you ask somebody in the interview a question, are they hoping that you can figure out whether they can reason in dynamically situations? What if they've already studied all possible questions that you will ask? This is exactly, we are in IIT Delhi, I'm from another IIT. We have question banks way before LLMs. We study the question banks and then we go to the exam and then try to see, and act very smart. If in fact that same question comes, you'll think a little bit, act as if you're thinking a little bit, and then blurt out the answer. And people outside can't tell whether you memorize the answer or whether you're actually solving from scratch. So how do you check that is the case? You have to do diagonal thing. You have to change the problem such that it's not likely to be in the memory. So one of the things we did is we changed blocks world by changing the names of the blocks world predicates, for example. So you could essentially take a blocks world which is on the right hand side, and then instead of calling it picking up a block, etc., you say attack an object, feast an object from another object, etc. It turns out these are different words, but it's exactly the same dynamics. And from logic, the predicate names don't change the actual semantics of a logical database. And you can do this also with random strings. And these are called the mystery or obfuscated domains. And you will notice that obfuscated domains in particular, LLMs die ignoble death. Essentially, they're extremely low, very low accuracy. And so that's basically got us to think that obviously LLMs, not surprisingly, that standard LLMs cannot plan when in fact there are interaction between actions. There are a bunch of other ideas such as chain of thought, react, all these things. We wrote papers on all of these. By the way, the first one was 3 papers in NeurIPS 23, one of which is a spotlight, and the chain of thought, another NeurIPS 24 paper. React is a TMLR paper, basically showing none of them actually do well for planning. Essentially. And in fact, for the chain of thought, one of the interesting things is if you look at that the last curve in the stacked curves, that is about an extremely simplistic reasoning problem called last letter concatenation. What is the last letter concatenation? If I give you 3 words, then you are supposed to take the last character of each of the words and then make into a string. That's it. Okay. And if I now told you this, then if I give you 10 words, you won't say, Rao, tell me again how to do this, because you understood the algorithm. You basically take the last letter of each of the words and concatenate them into a string. And if you do chain of thought, you would see that in the beginning, for the chain of thought examples that you gave, it actually improves the performance. But as the number of words increase, its performance falls down, which is one of the continuing things that you will keep seeing, that they don't capture the algorithm, they will capture, in some sense, the unfoldings of the algorithm to a certain length. That's what is going to happen with these sort of situations. It should not be surprising that chain of thought isn't working. Honestly, this guy called John McCarthy, who happens to have given the name artificial intelligence to artificial intelligence, mostly because he couldn't stand Norbert Wiener. Norbert Wiener had a perfectly good name for another area called cybernetics, which is basically what we are doing too. But he said, no, I'm going to call my field something different than what Norbert is calling. So he named our field. And he also said that, one major goal of AI is advice-taking systems. A system that can take general advice is basically an AI complete problem. And chain of thought, in effect, becomes, just advising the algorithm and LLM what to do in a particular problem. And the fact that it won't work should not be too surprising. You should be surprised that sometimes it seems to work. Now, having said this, one of the interesting questions is, look, we are writing this, that on these particular benchmarks, LLMs are dying, and we got papers, for the same people. In general, by the way, if you say LLMs are working, reviewer 2 is much happier than if the LLMs are not working, as Mohan Kankanahali tell you, because reviewer 2s, I keep telling people, are first-year grad students with one paper. Because the world has become so many papers right now that the reviewer pool is 99% first year graduate is one paper. And they're basically going to look at the papers they read and see if it is in the same thing, it must be good, otherwise it's bad, right? And it's not surprising. That's just a sociological phenomenon. But all these papers are getting in, they are saying this can work, and I'm saying the planning doesn't work. What actually is happening? It turns out planning really has 2 different pieces you can think of. One is sort of the planning knowledge, what actions, what are the preconditions, what are their effects, what are the possible previous plans and the databases of recipes that you might be having. That's the knowledge part. The other is, given a new problem, how to make sure that the plan that you put together doesn't have any interactions. That means one action doesn't undo what the other action is trying to achieve. This is typically what happens, when, for example, let's say you put on shoes before putting on socks, right? If you put on shoes before putting on socks, then you have to remove the shoes and you have to put on the socks and put on the shoes, and that's an example of interaction. So in general, you essentially will wind up realizing that there are these 2 parts. Classical traditional algorithms are actually very good for the interaction part, not that good for the knowledge. They assume the humans will write planning domain knowledge in some formal form, PDL and so on. LLMs, it's the opposite. They are actually good at knowing approximate domain descriptions, approximate strategies, approximate everything for any planning problem. But what they can't do is make sure that the actions that they put together won't have interactions, and so they can actually work without failure. How do I check this is the case or not? You take the blocks world, and one thing you can do is you can remove the preconditions in the blocks world actions. You can remove the delete effects so that actions can't get into each other's way. And then you check how LLMs do with this relaxed version. And we'll see that the more relaxed the domain is, the better LLMs are in actually giving the correct plans. So if things never can go, actions can't get into each other's way, then LLMs actually are just able to get it from the memory and splice them together, and that works already. And so you don't have to, you'll never be failing. So that actually is this particular example that shows. So this sort of gives you that standard LLMs are not particularly good for planning problems. And we can also talk about reasoning problems. So planning is one particular type of reasoning. And then you can put various patches to improve these things, but there are going to be limitations. Now, notice that when this was being done and we are publishing this, we were getting the pushback, as other people like Mohan might have seen, that no, LLMs can do it all. LLMs, the standard LLMs can do it all. Now, you have to ask yourself, if the standard LLMs can do it all, why do you need this new breed of LLMs called reasoning models? If in fact they're needed, that means you secretly admit that they were not actually able to do it all. Okay, so right now, as happens, we now have reasoning models. There's a new breed of models starting from O1, DeepSeek R1. They have been called the long COT models, long chain of thought models, and they seem to do better. In fact, even on our benchmarks, they seem to do better. And what I want to explain in the rest of the talk is to kind of figure out what has changed. Have they suddenly learned how to reason? Or is there some other way of understanding what's going on? So I'll provide a different interpretation for you. In particular, I'll basically say that there are two things that these reasoning models do that are different from normal LLMs. One is the two ideas. One is test time scaling. And actually that is very easy to understand. It turns out you can think of LLMs as generators of ideas. And if you have a verifier in the loop, then you have generate test. Generate test is the dumbest search idea. If you have taken intro to AI, that's the dumbest search idea you start from and try to improve search, okay? But that's because in those cases, you assume generator is a random generator. LLMs are not random generators. They are generators that are highly biased by the data they've been trained on. And to the extent we didn't put only mostly random stuff on the web, they're actually pretty good at giving reasonable, guesses for the problem. The real question is they don't know whether the guess is correct or not. And if you have the verifier in the loop, a verifier, that classical verifier that can check a plan and see whether it's correct or not, or a classical verifier that takes a proof and checks whether the proof is correct or not, a lean proof is correct or not, or a verifier that takes a piece of Python code and a bunch of unit tests, submits this Python code and a bunch of unit tests with a Python interpreter and checks if it is correct or not on the unit test. That is generate test with verifiers. That works, definitely works, because anything that is led through these verifiers, it's guaranteed that the verifier is happy with it, okay? And so now you're using LLMs for the generative capability and using verifier to ensure correctness. That's a way of thinking of test time scaling. And then the second idea is test time scaling is user facing. So you'll spend a lot of time trying to solve problem, generate and test until you get the correct answer in front of the user. What post-training methods do is do this all before the user even asks a single question, essentially generate a huge amount of synthetic problems, try to guess their solutions, tries to see if the verifier is happy with your solution, and then you have extra data, you can fine-tune the model with that. And if you fine-tune the model with that, you essentially have a better generator for that set of that particular new distribution. And again, it's not guaranteed to be correct, but it's going to be a better generator. It's more likely to have higher accuracy. This basically is a way of understanding what LRMs do. By the way, the word LRM is something we made up right when O1 came. We actually did our studies on the planning problems with O1, and we needed a name for this, and we just called it large reasoning models. And actually, the reviewer said, no, don't make up names because nobody agreed with it. So we removed the word LRM from the title, but then we left it in the rest of the paper. And now everybody calls them LRMs, actually. So it's kind of nice. But so anyway, so the last whole year, we've been mostly working on understanding, some of these two test time scaling and post-training techniques. So in a way of looking at it in this from this particular talks point of view is how did we go from system 1 to system 1+2, which is what kind of approximately LRMs are, and as I said, use them as generate test approach. And there's like a variety of approaches for trying to make LLMs generate more and more examples and then see more and more guesses and see if any of them are correct. A simplistic ones are, for example, if you're trying to answer a multiple choice question, you can ask LLM to generate its answer for the question many times and see majority answer. And that actually will have a statistically higher probability. It's not even a real verifier. But a much better idea is to actually have verifier, and in fact, a particular time of test time scaling that I am fond of, because we basically did most of that work, is this idea called LLM-Modulo. And what basically LLM-Modulo does is you have large language model as a generator, and you have a bank of critiques. These can be essentially, you can think of classical critiques, they can be learned verifiers, they can be classical verifiers, and they can even be learned as a normal, like a neural network or some other, hypothesis-based learning, or they can even be code-based verifiers where LLMs can actually suggest code, and you can improve the code with, again, one more recursive generate test with essentially the verifier being unit tests and the Python interpreter. So you can do that too. So imagine you have all these verifiers stacked up, and then LLM generates a solution, and then these verifiers all say we are fine or we are not fine. And if they say they're not fine, they can actually say what is wrong with the solution. All of this can be compiled into the prompt and then sent back to the LLM. Now, is the LLM completely understanding everything in the prompt? Of course not, but it does change the next solution that it outputs. And we basically show empirically that it improves the speed of convergence until you find a solution that essentially all the verifiers are happy with. So this is, in short, the LLM-Modulo. The kind of critiques, as I said, in the LLM-Modulo is they can be correctness critiques or style critiques. Correctness critiques basically cannot be done by LLMs themselves. Style critiques, LLMs are the only game in town, because checking whether it is, it's a correct answer is different from is it well phrased answer. And for the well phrased, the style part, LLMs are actually good verifiers. For correctness, they're not actually good verifiers. We have a paper in IIT in Singapore last year, basically this year actually, showing that thinking that LLMs are better at verification when they are actually bad at generation is one more of these misunderstandings of misapplications of complexity theoretic insights into LLMs, because generally verification is cheaper computationally than generation, but that doesn't necessarily mean that it's any easier for LLM. One of the things you have to understand is LLMs, as we saw from that IMO versus left shoe, right shoe example, LLMs can do very well, high accuracy on pretty hard problems while having low accuracy on pretty easy problems. So in fact, it really is more of a memory effect than the computational complexity of the problem. So for correctness, you actually have verifiers from outside or learned verifiers, and for style you can use LLM-based ones. Critiques can be binary. They can just say try it again, or say try it again, here is something wrong with your solution. They can come from external sources. They can be learned, as I said, and then there's a lot more detail about how to combine the criticisms from the various critiques in a meta controller to put it back as a prompt to the LLM in the next iteration. And we basically show that this is an ICML 24 paper. We show that LLM-Modulo actually improves performance of standard LLMs and guarantees accuracy. For example, if you provide verifiers for your domain, and in a variety of different benchmarks, including our benchmarks and other ones from planning and so on. And there's a there was like suddenly one of the things was planning became a lot more sexy again because LLMs can't do it. Honestly, that was one of those interesting things. And so basically everybody was reinventing stuff that we kind of knew. And so in fact, Google actually made this thing called natural plan benchmark. And it's not even planning. It turns out it's scheduling. The difference between planning and scheduling is the planning essentially contains actions which have preconditions. Some other actions have to make them true. Scheduling is essentially a classic resource allocation problem. One can be written down as a constraint satisfaction problem. Other has to be written down as a path planning problem if you're doing normal computer science settings. And anyway, we show that LLM-Modulo does very well on these sorts of benchmarks that they have made. One other thing I want to mention is I could have done a slightly different thing, which is take a planning problem, let the LLM convert it into a formal representation like the PDDL, and then give it to the planner to solve it. There are people who do this. I specifically choose not to, because I think that is undervaluing what LLMs are good at, essentially. And in fact, the classical solvers are not that great anyway, because they can't essentially solve problems in efficient enough time. And also, if you make additional constraints of different types, you have to write a new planner. If you have like a classical planner, you have temporal constraints, you have to then write temporal planner, and you have to keep changing the solvers. What I see is critiques are composable, verifiers are composable, solvers have to be written from scratch every time. And so we actually are very much into using verifiers in the loop from LLM. And those of you who are keeping track of what's going on, this is preceding RLVR. And RLVR, as we'll say in a minute, is nothing but LLM-Modulo applied in the training time and then using RL to kind of fine-tune. That's it. Okay, so those are the verifier parts. So we actually prefer verifiers to solvers. We don't want to just give it out to somebody else, And then the soundness, completeness comes from the verifiers properties. And one thing that I mentioned to you earlier is that LLMs cannot do self-critiquing automatically, and we show this in this ICLR paper, where we show that if you make an LLM verify its own solution, and then keep generating solutions until it actually get a correct solution, its performance counterintuitively, the accuracy as judged externally, can worsen. Why? Because it can wrongly assume that a correct solution is incorrect and continue to change it. This is the problem if you can't verify. You generally are worried that you can't verify the incorrect solution to be incorrect. But you can have the opposite too, that the solution comes and bites you and you can't tell it's a correct solution. And in fact, this is exactly what happens, because verification is a reasoning problem in general. Okay, and so basically we show that LLMs cannot self-critique. So if you keep hearing LLMs as judges and they can do all this, you have to keep this back in mind and say, what's Rao saying? Because this too is an ICLR paper. These two actually, in fact, is something they have to get through, extra reviewing, right? Because people don't want to believe that LLMs can't do anything. So anyway, on the other hand, they're great for style. In fact, there's a Comb paper last year, we basically show that if you use, for example, a bunch of behaviors, all of which, reach the goal, but some are more desirable than others, according to humans, and how are you can you kind of critique it? And in general, capturing what is pleasing to the humans is this style problem, and it's a much harder thing. And we actually show that LLMs are much better than pretty much anything else that we have. We have no style detectors. LLMs are our style detectors, essentially. So what we show there is, in this case, VLMs basically take these trajectories and critique, for example, saying for the last one on the left-hand side, that, okay, you're giving a pair of scissors with a pointy end towards the person, and probably they won't like it. I mean, the last thing in life that you want is a hulking big robot giving a pair of scissors with a pointy end towards you, because you will be very worried. And again, you will say, well, that can be written as a rule. The problem with style is those of you, all of us know, right? I mean, one of the things that impressed me most, and I can say this and you can understand it, when GPT 3.5 came along, is the damn thing can't make a bad English grammar sentence, a sentence with bad grammar. You and I know that we are extremely good at making bad grammar. We try our best to speak second language, and it's like the grammar is not rule-based, and it's like basically there are exceptions to exceptions to exceptions. And the only way you can write it right is to actually live and breathe the language. And we had a hard time, but LLMs could do that very easily. So in fact, the only way I could make it write bad grammar words is please write it as a first-year Indian grad student or something. And so if there is enough data from that, then it can actually sample from that. So style is something that we had hard time capturing. LLMs are actually very good at it, and we should not lose that track of that. And so sometimes you might want to critique the style too. So when people say LLMs as judges, what they really saying is, oh, the essay improved in style because LLM kept looking at it. And so it's a much better style thing, but a better style thing can still have errors. Accuracy has nothing to do with style. So in some actual sense, I mean, and you know this already, right now we all, especially faculty members, are sick and tired of seeing ChatGPT emails. Please don't do it if you're students, okay? Because we can see it from like 10 miles away. So please write it in bad English, whatever English you know, that might actually differentiate you from everything else that looks like this quote unquote AI slop, because it all has this nice, pleasing, bland style. And so in general, the style part is something that LLMs actually can generate as well as capture, and that's a useful thing. Anyway, So again, in general, I would say that LLM modulo is actually a good way to think of using LLMs in reasoning scenarios, in test time scaling. This actually also works for alpha proof. It also works for all the program synthesis stuff with the unit tests and the Python interpreter. And that's basically the verifiers there. So that's me saying, you can debate me that there is no other way. It's not like LLMs can just, there has to be an extra signal coming from verifier. And this is not controversial at all, given now that's exactly what is happening in the post-training that you're seeing. So the problem, of course, with the test time thing is now we actually used LLM modulo verifiers to make sure that they can solve reasoning problems correctly, planning problems correctly. Okay. The problem, of course, is they're going to spend time after you ask the question. And we have gone famously impatient. We want to hit return and get the answer so that we can complain it's not correct, right? That's basically what we are right now. So how do you improve performance? One of the things this guy, Marvin Minsky is another of the founders of AI, basically said is intelligence is integrating test part of generate test into generate part. This is a great thing to think about. All I need to do is whatever I am doing in test time, try to do it more in the training time so that the generator becomes better, so that I'm more likely to not fail with the verifier. Okay, so that's exactly what is happening in most of test, post-training approaches. So in fact, if you think of this LLM modulo, my version, imagine it solved a problem. Then you actually have the correct solution. After trial and error, it got a correct solution. It now becomes problem prompt, correct solution. That's part of the fine-tuning database. And then you can now fine-tune your LLM. Essentially, how you improve an LLM generator is fine-tuning. There are variations of it. RLL fine-tuning is actually very similar to SFTL fine-tuning. I might get into it today, but I'll actually go into it a lot more tomorrow in SES department talk. But in general, it's a kind of a fine-tuning after you solve the problem with like LLM modulo or like generate test sort of things. Okay, so that brings us to post-training. Post-training approaches essentially try to generate a huge number of synthetic data problems, synthetic planning problems, let's say, and then try to make solutions up for them and see if the verifier actually is happy with them. And if so, then they have a correct solution. So one of the interesting ways of thinking about it, like a mind bend, is LLMs were already good at dealing with all the declarative knowledge we put up on the web. That means stuff that we read in English or whatever language. We also had put procedures on the web, such as verifier code, etc. They don't actually, the standard LLMs are not good at exploiting the verifier code. They can just basically also take it as data and try to predict the verifier code. So in fact, the same LLMs, which can't verify if a plan is correct, can guess a verifier code. Those are two very different things, and they can do the second, not the first. And most of us think if you can't even figure out whether a plan is correct, how can you write the verifier code for the plan? Because that's a different thing. They've been trained on the verifier code, so they're more likely to output the verifier code correctly. Okay. So one of the interesting things essentially is that the LLMs essentially generate this. So basically, they are in the post training. What you're doing is you are, with this kind of approaches, you have now figured out a way of also learning from the procedural knowledge of the humans. Before we could only learn from the declarative knowledge of the humans, now we can also learn from the procedural knowledge. In which case now LLMs can basically use every bit of the humanities knowledge. That is the thing that we currently are. And post-training can be thought of as essentially doing that second step. That's a way of thinking about it. Now, in terms of once you solve the problem using some kind of a generate test approach, and in fact, those of you who know DeepSeek R1, it does a poor man's version of LLM-Modulo. What it does is it generates K trajectories for the problem and sees if any of the K trajectories end up in the correct solution using a verifier in the loop. Okay, now think about it. If the K trajectories are all wrong, then you wasted the problem because you're not getting any signal for the RL. Okay, so whereas LLM-Modulo will solve it until the problem is solved, and then it actually gets the signal from the correctness, and then you can then fine tune it. And so anyway, reinforcement learning in DeepSeek R1 can be seen as a watered down version of doing this sort of generate test. and then getting a solution that is correct, and then using fine-tuning methods. So anyway, when this is all happening, back in last year, I was giving this talk, a version of this talk, up until this point approximately, I would say, at ACL as a keynote. And after that, Noam Brown, basically, right after that, August I did this, and September 12th, I remember, is the day when O1 came out. And so he tagged me and said, Rav said planning problems can be solved. O1 actually can solve these planning problems. Now, this other stuff as to how it has actually happened is my reconstruction. But the chronology was I come back from ACL, there's this new model in town, and it actually, we had to check whether it is working or not. And since he tagged me, so we actually looked at, and those days, by the way, O1 would cost a lot more to access. So using our meager funds, like we had to pay $8,000 over like a couple of days to essentially check the planning problem benchmarks that we have and to see whether or not it's actually able to solve them, and to what extent, is it able to do it for standard ones versus the obfuscated ones, and also how is it doing when the length of the plans increase. That means you make the problems harder and harder. And so there are two papers, actually. The first paper that came out in the September, that week itself almost, and then the second one is a longer version that's in TMLR. LLM below. One of the things that you need to think about essentially is this inverse of order distribution, which essentially is, we were talking about it yesterday too, machine learning always had this issue as to, you learn the distribution and then you do badly out of distribution. Now, one of the things LLMs did is, what do you mean out of distribution? We'll make everything in distribution, and so there's no out of distribution. If your world is in distribution, then there's nothing out of the world. There's no separate web that somebody put under lock and key somewhere, right? Everything on the web is already in distribution. That is part of the reason why they don't seem to have this out of distribution problems, because we made everything in distribution to some extent. That doesn't work for reasoning problems, because for a single reasoning problems, there can be infinite number of unfoldings of infinite number of blocks word plans. And if you don't learn the algorithm, you'll just keep actually improving. You have to keep doing this, recursively fine-tuning, and that's basically what happens in some of these reasoning models. We also checked DeepSeek R1 that does, pretty comparable when it came in January, and it's also open source. They actually wrote a paper, so we can check that whatever I'm saying actually makes sense with respect to DeepSeek. And in April, Apple guys did something very similar. For some reason, they didn't read our paper. But in one of the ways the world right now works is, if there is somebody from a company, you would say the company did it, as if Tim Cook stops doing stuff and starts writing AI papers. And so Apple paper shows that LLMs have this problem. Except we've shown this like already as soon as O1 came, which is fine. So I got to do some bit of mid-hovering, saying, look, we did this before. but I also have good friends in New York Times. So when New York Times wrote an article on this paper, I made sure that they showed that we did this first. So we got that point taken care of. One other last thing I want to mention before we kind of slowly conclude here is LLM-Modulo. Remember, we had LLM as the generator. Now we have LRMs. What if we do LRM-Modulo? Remember, the way I described it, LRMs are just better generators. They're not guaranteeing correctness. They just more often correct. If your life depends on having correctness, you still have to verify separately. Okay? So what if you do LLM-Modulo except with LRM as the LLM? So that becomes LRM-Modulo. Okay? So LLM-Modulo is like you put O1 to generate suggestions, and then you would actually have the verifiers checking whether the solution is correct or not. And if you do this, it's basically the same exact thing except with a better verifier. And it in fact improves. So basically, and one of the other things you have to think about is most of the models, when they're post-trained, they no longer do any test time scaling. I understand a lot of you think, oh, people have been talking about this intermediate token generation as test time scaling. That's total bogus. In fact, tomorrow I have an entire talk on that in the CS department. I'll go more into that. But essentially, test time scaling really is more like verifying or taking like n solutions generated and seeing more of them correspond to a particular choice, etc. They don't do that. Normal, R1, etc. And in terms, something like LLM-Modulo basically does test time scaling as well as post-training. And not surprisingly, it improves performance further on O1 and now with guarantees, because if the verifier says you're good, then you're good. So in general, I would actually say that if you want to extend the reasoning model train better and better to your domain, come up with good simulators, good verifiers for your domain. Do you see what I'm saying? And then put them in a loop with the LLM and then post-train them. And that's how you actually do performance. Pretty much this is what everybody is learning. It's just that we were a little earlier, and so we were seen as a bit of Cassandras, but Cassandra ultimately was right, if you remember Greek mythology. And so this is the reality. And again, please don't take this as anything negative about LLMs. This technology is amazing. And you don't need to add more made-up stuff to make it even more amazing than it already is, because it actually puts at our fingertips, especially given that we don't seem to care about the training costs, that we leave it to Sam Altman. This is at putting at our fingertips humanity's knowledge. And so it's a useful thing to have. Okay, so this is actually almost my last slide. I want you to think about a very different way of looking at LLMs, very weird way of looking at LLMs, but I actually like it. LLMs and LRMs are an amazing 21st century refresh of expert systems. We're supposed to hate expert systems. We're supposed to say, oh, expert systems are no good. LLMs are so much better. What's the important thing about expert systems? People had to give knowledge, and the expert systems will then pick that knowledge up and come up with the solutions. Where do you think LLMs are getting their knowledge? Your traces. I understand that if Sam Altman said, look, Satya gave me money to construct, got enough of the compute power, I just need the web. Why don't you guys make the web up? We'll say, screw you, we don't have time. But we already made the web. We put everything we know on the web, essentially, for each other. And then LLMs just basically use that to essentially train on our footprints of our knowledge. And as I pointed out to you, now with the LRMs, you can actually use both the declarative and the procedural parts, okay, with problems, but they can be used. And so this is a great way of thinking of this 21st century expert systems at your fingertips. But the thing that you have to remember is the best this will get to is that LLMs and LRMs would still stay in the humanities knowledge closure. Okay, there's a bunch of words there. A deductive closure essentially means we give a logical database where it says A implies B implies C. The deductive closure of that is A, B, and C. Because A is true, A implies B becomes true, B is true, B implies C is true, C is true. So deductive closure, full thing is like ABC. So based on what I know, then I should also be able to generate what else follows. That's typically is what's called reasoning problems. LRMs essentially support to some extent, with if only imperfectly, as I explained to you. how to do this. And now with that, you have the ability to exploit both the declarative and the procedural knowledge of the humanity. But the interesting question, and that's a very useful thing, especially for domains like math. Math is famously sort of, what's his name? So math is famously sort of in the deductive closure. In many parts of it. And so in that particular case, actually, it's not surprising that we're doing very well with the math. Where things become interesting is people say LLMs actually can just do automated science. They can be extremely useful for a working scientist. But science in general is extending the humanities knowledge closure. Okay, that obviously is not something that's part of the game. And when people are impressed with LLMs, it's because they figured out what the humanity already knows. To actually do science, you need to figure out something that the humanity as a whole is impressed. And if it's in the deductive closure and you haven't yet computed that, that's what is happening in math. Like they found the proof for Aodo's 15th problem or something. Those are easy. But Kurt Gödel notwithstanding, and of course Kurt Gödel is still staying there saying, Rao, you're wrong. But that notwithstanding, a lot of math really is essentially in the deductive closure. And that is something that LLMs can support. So LLM revolution is amazing, but completely ignores the cost amortization considerations. Right now, we don't care how much time anybody has spent in training these models. We complain that he's wasting time, he's taking token cost per each token. And because of which, in fact, efficiency with LLMs has come to mean the number of intermediate tokens generated in the reasoning models because you're paying per token. But really, the question of whether or not the time spent in the training is actually made up in the amount of time the amount of times you're using it in the inference stage is still up for grabs. For example, from a classical search perspective, if you are ever supposed to ask what is the shortest path from S to G in a large big graph, a much simpler thing to do is first do all pairs shortest path for that entire graph and keep that in a big table. And then say, now that I've done that, the shortest path from S to G is this. We don't do it because we solved a much harder problem just to solve the easier problem. But you would do it if, in fact, this SG is just one of the times you're being asked, and somebody else will ask S dash G dash, somebody else will ask S triple dash 3 triple dash. So who does also shortest path algorithm essentially hierarchically? Google Maps. Right? Because they don't know, randomly Rao wants to go from the Grand Hotel to IIT Delhi campus, somebody else wants to go from somebody else. Instead of just solving it every time from scratch, you might as well just do all shortest path up front, and then that gets amortized. That's what computer science tells us about amortization, and we don't really know whether LLMs are doing it right now. We're just letting them pay, and so the question is whether, in fact, we can figure out this amortization before the bubble bursts, is anybody's guess. And then finally, will we be talking about LLMs 5-10 years from now is a very interesting question. They're amazing tools. There are certain kinds of things that are basically bringing to us, but obviously they also are not the answer to everything that you might be interested in solving, especially, as I said, they never, for example, learn algorithms. They learn the unfoldings of the algorithms, even as we're saying. And the other thing is they don't generate their own experiences. They are dependent on our experiences. When people say LLMs are world models, they have a model of what you think about the world as you have written on the web. Okay, and that may or may not be the actual world model. That depending on, especially given the noisiness of the data that's been captured, and it's useful to keep in mind. So again, agentic systems are all over the place, and so much of my discussion is about planning. An agent has to do plans and execute them. And so what I'm saying is, be careful that if the world is non-ergodic, you need to make sure that there's some verifier in the loop, or the failure cost is low. Assuming that it's 99% of the time correct, so it's good enough in my domain, may not necessarily be a great idea, because the failure can be catastrophically high cost, and that it will just completely change the equation. You guys know that the dirigibles were the way people were flying from continents to continents, and they were actually doing quite well people were going in Hindenburg. Everybody thinks of Hindenburg as a bad thing. It blew up. Before that, it came all the way from Germany to New Jersey with people sitting in it. You forget about that. The problem, of course, is you don't get to say, well, look, I mean, all these people came all the way. They just, there was a small glitch in the last minute. They all died. That's not enough. So even though there were many, many times it went back and forth, that failure was enough to actually kill the Hindenburg, I mean, the dirigibles industry and start the airplane, fixed-wing aircraft industry. So those are the kinds of costs of the failures that you have to take into consideration. If not, if you just go ahead and say agentic system, it's going to work, it'll work for a while until the first failure, and then all bets are off. So in summary, I basically try to show you that LLMs trained on just web corpora, that is standard LLMs, known to have severe limitations on planning and reasoning tasks. This could be, but they could be very good arbiters of style. They could, however, be used as generators in a generate test cycle to give robust planning performance. That's LLM-Modulo. This can then be compiled into the generator in the post-training phase, and then the resulting LLMs will still have no correctness guarantees, but are much better generators. And post-training incrementally compiles verifier signal into the LLM. That's the way of thinking about it. And then the last thing that I don't have time at all right now, but if you found any of this interesting, show up for my talk again tomorrow, which is basically this particular one, that if you go into LRMs, there is a whole bunch of interesting new misunderstandings about them. It turns out that all of them generate a whole bunch of intermediate tokens before generating their solution guess. And people tend to assume that these intermediate tokens have meaning, and it tells us what the LLM is thinking. It's like reading the God's mind. And we basically show, we had about 7 papers in various workshops at NeurIPS, and I also did a keynote talk in one of the workshops, basically summarizing, which I'll be redoing tomorrow, showing that the intermediate tokens are helping the LLMs, but they don't necessarily help the humans at all, and they don't have to. They essentially can actually be not even in English, they can essentially be points from the embedding space, and some points in the embedding space correspond to words, some don't at all, and they can actually talk in terms of those two, and you can actually improve the accuracy that way. I'll talk more about that, and also this whole issue of RL post-training versus SFT. It turns out that DeepSeek R1 basically made RL very popular again, except it's a very weird bastardized form of RL, where in normal RL, if you get outcome reward, and you have a bunch of decisions that led to that outcome, RL has to figure out who gets how much of the credit. What DeepSeek R1 does is, if you are in the winning team, you get a certificate, the same certificate everybody gets. That essentially makes it SFT, because what SFT does is everything that leads to the solution is equally worth imitating. That's what RL does exactly. And so there's a whole bunch of cottage industry of papers, especially in this NeurIPS, saying RL has this property, RL has that property. What they actually mean is this weird version of RL, which is actually SFT, has this property. In particular, in the way of doing it this way, it turns out that RL is incentivized to speak longer if the solution is not likely to be incorrect, and speak shorter if the solution is correct. And that has been misunderstood as RL is improving thinking, okay, in general. There's a whole entire set of things about these intermediate tokens that I can get into, and that's almost a second order version of this. But I wanted to do here more the issue of where did we go from LLMs and to LRMs, and what we can expect. Thank you again for your, first of all, waking up, and secondly, your attention. Thank you very much.
Thank you, Professor, for such an interesting talk. So the floor is open for questions now. Any question? Yeah.
Thanks for the nice talk, Professor. Can these LRMs or LLMs, can they reason that why they are not able to reason a particular thing?
Okay, so here is one thing that I can say about LLMs, okay, before answering a question, that unlike classical solvers of any kind, LLMs, for example, can guess a plan. That can be wrong. They can guess a They can guess a domain model. That can be wrong too. We actually have a NeurIPS paper showing if you don't want humans to spend time writing the domain models, you can have LLMs guess the domain model and do a kind of an LLM-Modulo approach, trying to kind of improve the domain model until the experts are happy, and then use that for then the solvers, for example. They can also guess abstract policies. One of the things that people don't realize is the entire RL essentially tries to start from pixels and then tries to generate abstract strategies. Extremely costly thing to happen. We did this once evolutionarily, but it's very, very hard to do it again for these systems. With LLMs, it actually can provide an abstract strategy just as easily as it can provide a plan. So for example, in blocks world, I can prompt an LLM, and you can go back and ask, don't solve this blocks world problem. Tell me what would be the kind of strategy I should be using to solve blocks world problems. And I wouldn't be surprised if they'll say one of the well-known strategies, put all the blocks on the table and put them in the right order as it is in the goal. Right? That's an actual abstract strategy. And you and I can talk about it and understand it. And they can do that mostly because they're not going from their own experience to build the abstractions. They're actually going about with our abstraction that we have put up. Okay. So having that as the background, your question about can they kind of guess that they will have trouble about reasoning in this particular case, yes, they will guess. They will never shut up. Any question you ask, they will give an answer. Okay, and that's actually a very useful thing, because normal classical solvers would not say, they'll say that's not my department, somebody else's department. This thing will never shut up. But the guarantee that they are correct is bad across everything. It's not somehow that they are more incorrect for the easier problems and less incorrect for the harder problems. There is no such thing. Okay. Again, in general, they will give you an answer, and you can, if that's interesting to you, you can check. This is one way of saying LLMs can do meta reasoning. They're imitating our meta reasoning capabilities that we have thrown into the data, and they can reflect it back to you. And sometimes it's a useful thing because there is no other kinds of approaches like that.
I have another question. So it seems like for the knowledge case, when it's doing something, like when it's generating something, and it's not related to the reasoning, it's related to the knowledge, like it's hard to predict something, generate something. So what happens is, it seems like there's some self-reservoir, and like you mentioned it, approximate retrieval. From what I was able to interpret is, it's actually seeking inside it and picking something up. For like the SFT part or the RL part, is it also sort of building some form of reasoning-based reservoirs within itself and picking out from there, or like
So no, okay. First of all, the two issues. One is that what you kind of, the closest you're coming to in terms of what I was talking about is trying to understand what our LLMs are doing in terms of the memory. And that's a very, very useful thing. I would argue, and again, I'll get into it more details tomorrow, that you should think of intermediate tokens as LLM talking to kind of basically LLM's effort to try to answer this question with respect to something that it already knows. How many of you know the mathematician's room getting on fire joke? So a mathematician was sleeping one day. He smoked and he left the lit cigarette and then went to sleep. And then he wakes up in the middle of the night, the room is on fire, part of it is like the stool is on fire. So he needs water to put out the fire. So there's a glass, but the glass, he's already drunk of the water. So then he has to get up, go all the way to the bathroom, fill the water, fill the glass, and then come and pour it on the fire and goes to sleep. 5 days or 6 days later, again, the same exact thing happens, because this is mathematicians, so they're always smoking and trying to do random things, right? So, and then this time he wakes up, he finds that there is a glass full of water. So what he does, he pours it out and then puts it on the floor and says, now it's reduced to an already solved problem, and goes to sleep. Okay? Now, think about that. As funny as that joke is, and you think, what LLMs do is essentially that. And let me illustrate that by something that I'll talk about more tomorrow. We basically show that if you track, in this picture there, we have shown, we train an empty transformer to solve essentially arbitrary maze problems. Okay? And then basically, and it has pretty high accuracy, 90% accuracy in that distribution of those sorts of maze problems. Then we ask it essentially to solve this one, which is a maze, which is no maze, like S and G in the free space. Okay, it's a trivial problem. LLMs basically die, and they don't die just by saying, oh, and stop. They will talk until the entire context window is blown out, and then they'll give the wrong answer. Okay, so that essentially tells you that they were desperately trying to kind of solve the current version using the versions that they've seen rather than solving the current version from scratch. So this is why I keep thinking that the computational complexity of the underlying problem is a completely wrong metaphor. And when people try to improve the efficiency by reducing the number of tokens, think of that as rearranging your spice rack so that, for the kind of food you are making, there'll be fewer movements to find the correct spices. That basically is what they're essentially doing in redoing this sort of retraining such that the intermediate tokens can be reduced. It has nothing to do with the underlying problem complexity. It is for this set of problems, can I get the solution by assembling what I have faster?
So it's basically doing the self-predict, or if it's doing it after it's predicting the output, not prior to it.
They don't do that. In the inference stage, there is no such thing. So by the way, there's this one entire thing that I'll talk tomorrow about the fact that the LLMs in the intermediate token say, now let me backtrack, now let me reflect, etc. People think that means they're actually doing that. Okay, I have an example of that. Again, I'll talk about tomorrow what I was saying last week. Imagine I'm a lazy guy who has been asked to, bodybuild. So I have decided to have like a physical instructor, but I'm doing it by phone. So the instructor says, now Rao, do 8 crunches. And I'll say, 8 crunches done. Then I will say, now Rao, lift yourself with one hand. Lifted myself with one hand. Do you know from that I have done this? No, not at all. And are essentially the same thing with LLMs. They imitate everything, the style of everything. To the extent there is any chatter about intermediate tokens in the training data, it would be the ones that people said. They will say exactly those kinds of things, right? That doesn't necessarily mean that they're actually doing it. And you can actually make them solve the same problem without saying anything like backtracking, etc. That is one of the points that, trying to look at the intermediate tokens and say, oh, now this says LLM is self-critiquing itself, now it is backtracking. This, my sense is it's all pseudoscience right now, unless I'm proven otherwise. And I'm going to call it. In fact, tomorrow I'll call it even more, but essentially, right, I'm trying to kind of get 3 of you or 4 of you to show up to tomorrow's talk too, so that we can have a second part of this whole talk. But essentially, that's where, I think, I don't think they're actually self-critiquing. It's just that they've been trained once. And, and then these intermediate tokens can be thought in terms of prompt augmentation that increases the probability of the solution. We can have more conversation on that separately. Shantanu.
See, I have a very general question. That is, say, the structural causal model is also being used for various kinds of formal construction of results and other things. So, and they're also talking about causal generators and causal generated models. So how do you place those words in the context of what are you doing?
So in general, causality, there is no causality without intervention experiments.
Absolutely.
Right? Unless you're just copying. So by the way, I can read up, I can make Yuda Pearl's textbook part of my training data, and it will say structural causal models. And that doesn't necessarily mean that actually the way you generate a causal model is basically from experience, and and then there is no such thing. Essentially, they are just dependent on our ability. So I don't know. There's an entire direction in terms of how causality matters, but I don't have any clean. I haven't seen any clean work that's somehow changing how LLMs work from that perspective, because it's not like they're doing any separate experiments. If they're not doing separate experiments, where are they getting the data other than beyond what?
Is there an alternate to these in technology today where it's moving? Because it's
What?
finally Ngram and
Yeah.
basically filtering on top of Ngram outputs.
Yeah, but what I'm saying is there has to be a signal. Somebody has to do this experiment. So one of the things that happens in the tool calls is essentially they are generating their own experience by calling outside. That would be the place where it will start happening to some extent. But mostly right now those are being done in very benign situations. There is a thing called
Very small problem.
Not only that, it's more interesting. It is benign situations. There's a thing called tau bench that those of you who are into agentic systems have heard of. And so when I kind of moonlight with MSR and somebody was talking about this stuff and I said, hey, can you tell me what are all the places where there are action interactions? And they said, no, actually they remove anything with action interactions from the training data. So it is basically making sure, at least in the training data in terms of testing, etc., making sure that you're only looking at actions which are essentially have reversible effects and also you are in ergodic worlds. And then you then put it in the big bad world, and I don't know how many of you saw this poor guy who used anti-gravity, which is GPT 5. I'm sorry, it's Gemini 3 Pro's agentic system, and which essentially did a large amount of thinking aloud and then essentially completely erased his D drive. And unfortunately, you can't undo that. That's a non-reversible operation, right? And so this business of when you do experiments in the real world, then you take into account the possibility and that you can actually create pretty bad outcomes, and there have to be significant sandboxes that are built. And the problem is experiments in simulators are not real experiments. Now, one of the things that I keep telling people, and those of you who have any background in RL, etc., and think, oh, simulators are very nice to have. Somebody wrote the simulator. There are no trees in the IIT campus that have simulators growing. Do you see what I'm saying? Somebody understood the domain and wrote their understanding of that real world domain into a simulator. The same person could have potentially written a model or a verifier for that. Okay, so it's if you are only testing in the simulator, that doesn't necessarily guarantee that you're getting new knowledge at all, because the simulator is essentially written by somebody's understanding of the world. And true experiments would involve actually doing it in the real world.
Any other question, comments? Okay. So thank you, sir. Thank you for visiting us, and thanks for delivering this keynote.
Thank you.
May I now request Professor Sripat? May I